Hi, welcome back for another video with the Casio VZ-1. Today I want to look at how ring mode works, and the way I want to do this video is to capture some audio on the machine and then to go on the computer and see if we can recreate those sounds with pure data. So to do a good experiment, we should check our experimental settings. So let's go through the settings here. We're only going to use oscillators 1 and 2, and they're in ring mode, so that's what we want. Both are set to sine waves, and right now both have pitch 1. And we need to be careful about the levels. So you see here the sustain is at maximum level for both oscillators. The envelope depth is at maximum for both. And there's no velocity or amplitude sensitivity going on. Okay, what I want to do is to capture different combinations of oscillator pitches. And I'll start with oscillator 1, and I'll go from 1 to pitch 5. Then I go back to 1, and then we go to oscillator 2, and we go from pitch 1 to pitch 5. And well, if you turn both oscillators off, you hear nothing. So we've got to have at least one on. So let's start with oscillator 1 on, and I'll go up through the pitches. Now let's do that again with oscillator 2 instead of oscillator 1. So that does nothing, which is kind of what the manual says would happen actually, but I wanted to do it just for completeness sake. Now let's turn both on. Okay, so that was going from 1 to 5 with oscillator 1. So now let's start changing the pitch of oscillator 2. And we go back to just listening to oscillator 1. Okay, now we do just oscillator 2. Which is just a sine wave going up the harmonic series, what you'd expect. And now let's have both. Cool. Let's see what the audio looks like on the computer. So we're back at the computer with the audio I just recorded at the keyboard. I've taken the movie recording and edited out the bits where I was talking. And this is just the sounds themselves that we got out of the Casio. So just let's go through them again. First we do ring mode, and we keep the pitch of oscillator 2 constant at harmonic 1, and we step through the first 5 harmonics on the first oscillator, and that sounded like this. Now, straight away, I want to point out something odd that is happening here. If you know how ring modulation works for sine waves, then you know that what you would expect, the expected outcome, if you take two sine waves, is that you get the sum and difference frequencies. So here, two sine waves have the same frequency. So the sum is 2, and the difference is 0. So you only get 2 times that original frequency. And then here you get these two, and these two, and these two, and these two. So what's going on with these frequencies up here? That's one weird thing that immediately jumps out. Like, these shouldn't be here if this was ring modulation of sine waves. The second bit is listening to the second oscillator while I'm changing the pitch of the first oscillator, and we can clearly see that that changes nothing. And here we are listening to both oscillators. The pitch of the second oscillator is constant. The pitch of the first oscillator starts at the same as the second, and then it steps up to 5 times higher. Now what the manual says is that if you mix both oscillators in ring mode, then you get the pure sound of oscillator 2 and the ring mod sound. So if you would naively believe the manual, you'd expect to see these tones and these bright 2 tones here. And indeed we see that here. So we see the same oscillator 2, the constant pitch down here, and then here is the second one. Here there's 2, here there's 2 above, 2 above, 2 above. But we get a bunch of extra overtones, and there are more overtones than last time, because look over here with the oscillator 1 set to the 5th harmonic, so everything is spread out the most. We naively expect these 2 and the one at the bottom. But here is a pair of sidebands, and here's another pair of sidebands. And I'm calling them sidebands because you can tell they have the same intensity, so they look like they belong together. So again, something odd's happening. Here we get extra frequencies, and here we get even more extra frequencies. And you can see that they start close together and they get spread apart. Okay, at this point in the recording, we're back to listening just to oscillator 1, and now we're keeping the pitch of oscillator 1 constant, and we're stepping oscillator 2 from harmonic 1 to 5. And again, something unusual is happening. These are the ring mod sidebands you expect, and there are these sidebands above, and you can see here there are sidebands at the bottom. So something funny is happening, and it's not the same thing as the first time around. You'd expect that these 5 tones sound exactly the same as these 5 tones, but they don't. There are extra sidebands that shouldn't be there, and they're in a different spot. Okay, here we are listening just to the output of oscillator 2, and we are stepping through the pitches of oscillator 2, so that looks predictable. Those are the rising tones. And here we get the combination of these 2 things. And again, it is not this, the whole is more than the sum of its parts. That's the expression here. Everything is rising, but the overtones are way denser than they are here. So this is just what we get out of the synth. This is the recording, and I found it very surprising to find this. And then I sat down and I tried to recreate this in pure data, which was hard, but I think I came pretty close. So let's move over to pure data. And let's do these 5 pitches to them. Actually, no, I can do the first 2 and I can do the 5th one. So this is this plane, this is the first one. You can hear that's pretty close. Here's the second one. And I didn't put buttons in here for all 5, so this is the 5th one. I think that came pretty close. And we can do the same thing here for the case of both oscillators enabled and the first 2 and the last pitch. So let's start with both at 1, and we bring up the level of the second oscillator. Sounds the same to me. And then we go to the second harmonic on the first oscillator. And then we can go to the fifth harmonic on the first oscillator. So I hope you'll agree that this is, while it's not perfect, it's pretty close. So now I want to show you how what I had to do to get this, which was surprising to me. So here is my recreation of the ring mod, and this spider web is a lot to take in, so I'll try to talk you through it. What's happening here on the left is oscillator 1. So there's a phasor and a shaper. And this first input is the frequency. So oscillator 1 gets a frequency, and that's oscillator 1. Here on the right, the sound of oscillator 2 is coming in as audio, but separately the control voltage for the level. So the audio of oscillator 2 goes here, and that gets scaled by its own level, but also by the output of frequency of oscillator 1. So that's how the ring modulation happens. Now, the big surprise is that here we're mixing in a third harmonic. So this is what we'd expect, but here's a third harmonic, and that third harmonic explains these lines in the picture. If you look up what the frequencies are and you sit down with the calculator, then you see that you can explain these frequencies and where they are by mixing in a third harmonic into the first oscillator. Now, the even weirder part is over here. So this is the series where oscillator 2 is mixed in. So when oscillator 2 is mixed in, we get a second harmonic, but the second harmonic is added to the first oscillator. So the level of the second oscillator determines how much second harmonic of the first oscillator we get. I can't believe I just formulated that sentence. I'm not going to try again. So somehow, and again, I worked this out by looking at where these bands are, where these sidebands are, and working back from how they might appear. It appears that the Casio VZ-1 mixes in second harmonic and third harmonic on the first oscillator when you do ring mode, which in itself is surprising and not anywhere in the manual. And then on top of that, the way they mix in the second harmonic depends on the level of the second oscillator, not that of the third oscillator. So just if you move up the slider of the second oscillator on the synthesizer, you don't expect to be adding a sound to the first oscillator. At least I don't, but that's what this machine does. Anyway, there's a download link in the description. You can play with this yourself. I think this is pretty close, and as crazy as this is the simplest explanation I could come up with of all these frequencies we see here coming out of the machine. And I think that concludes the video. Well, just for fun, I can play these last this last combination here. So this is what you get when you have, no, let's look at all of them. So if oscillator 1 is at frequency 1 and we multiply the second by 5, and then we first only listen to oscillator 1, then we get this. And I'm doing something wrong now because we start with 1 to 1. And here is first oscillator at 1, second oscillator at 2. And here is first oscillator at 1 and second oscillator at 5. Again, it's pretty close. And then over here we have both oscillators on the pitch of oscillator 1 is constant and the pitch of oscillator 2 is stepping up. So both are on, so we want this. This one is at 1, this one is at 1, and then we get that in pure data. And that agrees with the recording. Let's try a 2 here. Again, pretty close. And then with 5, we get that. There are too many combinations here to try everything out and to be absolutely positive that I got everything right, but I'm just relieved I got this close. That was it. Thank you for watching.